Hi, my name's Joe Nelson. I write the documentation for Azure Cosmos DB for PostgreSQL and for the open source Citus Postgres extension that powers distributed query execution. We're going to be talking about doing queries more easily, multi-tenant SaaS apps using object-relational mappers. So I guess the first most natural question is, what is an ORM? So Object-Relational Mapper allows developers to query the database using their native programming language rather than going directly to SQL. So these ORMs are available in pretty much every application framework. We've got Django and Rails over there on the side. And to give you an idea of what that means, writing it one way versus writing it another, first we have a select count star from users. That's the plain SQL way to count a table of users. And then we have the way that the Rails active record ORM would express it. You just say user.count. And so that can be attractive because it's shorter for people. In some cases, the queries are shorter. And then the second part is, now that we've talked about ORMs, what is a multi-tenant application and query? Azure Cosmos DB for PostgreSQL excels in several use cases. One of them is the multi-tenant use case. And what that looks like is generally SaaS applications that hold data for multiple businesses that we call tenants, and then it isolates the information from one tenant to another. So we talked about one part, the ORM part. Now let's talk about the other part. What are multi-tenant queries and what's a multi-tenant application? So Azure Cosmos DB for PostgreSQL excels at many use cases, and one of them is the multi-tenant use case. What does that look like? A SaaS app can often hold data for multiple businesses, and we'll call them tenants, and then they isolate each tenant's information from each other. So you could think of an Etsy or a Shopify. You're hosting storefronts for multiple merchants. When you're on one person's store, you don't want to be seeing products from someone else's store. Like, everything needs to be separate. And then individual tenants will query for their own data only, obviously. That's what we want to ensure, not the data of the others. And we say the queries are filtered to a specific tenant ID, so like a store ID. When we're writing for this use case, the multi-tenant SaaS use case with our ORM, really looking for two big goals. One is should be safe. That is easy to automatically scope those queries to tenants. There's no leaking from one to another. And that it's fast, that the generated SQL, when you write those ORM statements, it creates SQL code. The code that it creates should work efficiently with Azure Cosmos DB for PostgreSQL. And you might think that is easy, it's just standard SQL, but there are some things to be aware of that are specific to being in a distributed SQL database. In this case, it requires some special modeling and query techniques to maximize that query performance. This form of a database actually uses multiple machines, nodes, and those nodes work together to process your SQL. They all will do their part and kind of combine the results to go faster. But it's sensitive to small changes in the SQL itself. And combine that with, when you're kind of behind an ORM, it's generating that SQL for you. It's difficult to make those customizations sometimes. You're hiding behind that higher level interface. So we need something to bridge the gap. But we've made our two libraries, so far just two. One is for Django multi-tenant. One is for Rails, active record multi-tenant. And they allow you to write code in a way that you normally would, but translate your queries, the SQL that's generated, to fit really well with that distributed data. So let's check it out. We'll jump right into it. We're going to look at a simplified schema for managing stores, products, and orders. And I say simplified because in this little dream world, shoppers can purchase only one product per order. And we do that just so that the relationships are simplified, because it's kind of irrelevant to the understanding the concept of the code. So we're going to jump into the gray nondescript world of code here. We've got the three tables: stores, products, and orders. And we don't have to look too closely at each of these columns. This is just a data set that I had at hand and it seemed convenient. But we should make take some notes about it. One is, beneath each of the create table, we're running a function called create distributed table. That's what takes the table, breaks it into what we call shards, smaller sets of rows, and those shards get put onto the individual nodes. Each shard is stored in a single node, and another thing you'll notice is that the uniqueness, some of these primary keys are composite. because as a property, there's too much overhead in a distributed database to maintain or enforce uniqueness across machines. So in this case, the uniqueness is enforced at best per store or per tenant. Just a detail to be aware of. If we look at the way you would code this thing, we saw what's inside the database. And this is just the basics to tell Active Record what it needs to know about the data so that we can use Active Record's form of querying its own language to do it. Here we say, look, we have a store, product, order, just like before. They're all Active Record models, and we kind of declare the way they rely and depend on each other. That stores have products and orders, or that orders belong to products, so there is a product for orders. And then we declare the primary keys, which you'll notice are slightly different than I said, but we'll kind of correct that later. Okay, given we've kind of put the data in the database, we've told Active Record, generally these are the models we have to work with. Let's use Active Record to make some queries. And I thought a nice query would be, let's find a product, the product that's responsible for the most expensive order in a particular store. There's a lot going on in this slide. I'll just break it down. So the first line we have is a command in Ruby. We're saying, take the first store that you find and call it S. It doesn't really matter for this example which one. And then we see the result of that. It's found store ID 1. Its name is store A. There's a date that was associated with it at the time the data was created. And then we see the SQL that Active Record generated because of that query stored at first. It's essentially saying, give me all the stores, order them by their ID, give me the smallest ID first, and take one of those. Okay, so we've got S. And then we ask Active Record, okay, of this S, give me the orders, and then find the one with the highest value, the highest sales value. And this is sort of an unfortunate play in words here. We're saying orders.order, that just means order them, like sort them by the value, and get the most expensive one, and then find the associated product for that order. And you can see the result of this is a product. It has product ID 7, has a name, it's a MacBook Pro laptop. And I guess for in this case, there was an order which had a big batch of laptops, so it was an expensive order. As a result of doing this one command in Active Record, the Active Record is actually creating two separate SQL statements. Now, with some trickery, we could probably make this more efficient and make it generate only one. But this is still a really good example of how it's generating queries and the considerations of how it's doing and what we should do. First query it's doing is it's getting all the orders for the current store, and it's sorting by the most expensive one, and it's grabbing that one. With that in hand, it has the product ID inside of that result, and it uses that product ID to construct a separate query, a second query, looking through product, saying, which product is the one for that particular ID? Give me all the details about that. And that's how it constructs that final result of products. Okay. Now let's zoom in on that second, or I should say that last query. That's kind of where the trouble lies here. And there's kind of two ways that it's problematic. First, it's not as safe as it could be. If you look at the query, I've copied it again here. It doesn't filter on store ID at all. Now, in this case, it's okay. It's safe. It happens to work out. The order was already chosen from the right store. And so this is its product, presumably also in the right store. But really, it'd be cool if all queries always had that protective filter on the tenant, on the store in this case. Just whatever queries Active Record is going to be sending, they have a protective filter. That would just be a nice thing to know. Then no matter how fancy my queries are and tricky and big, they're always going to generate queries that are safe. So safety is an issue. And then the second problem is actually it's not as fast as it could be. And this is a distributed database thing because it didn't seem bad. The SQL is just pulling some stuff as it should. However, what's happening is when we make this query, we're saying, okay, distributed database, give us products. I want product 7. We did not tell it is the specific tenant, the store, because the tenant determines the shard that it's going to be pulling data from. And the shard is known in the metadata to live in a certain node. So the query planner, given just this, has no idea where this thing is. All it can say is, well, we have products, and I know there are 32 shards. That's the default. And so I'm just going to ask each and every one. I'm going to spin up a whole new query called a task, a little fragment query that's specific to a shard, and send out 32, send them out to all the workers and say, do you have product 7? Now 31 of them are going to come back and say, no, I have no idea. I don't have it. And one of them will be good, and it'll combine that information to give you the one. But it just didn't know where to send it. So we need to provide the query planner more information. So we've seen this, that using the standard active record with a distributed system like this and a multi-tenant system is not particularly as safe as it could be, and it's not even as fast as it could be. So rather than having you try and mess with active record, Django, we created some libraries for it. Now we're focusing on the active record Rails one right now. We called it active record multi-tenant. And here's how we'll pull it in to take our original example and make it work better. It doesn't really change the length of the code much at all. We just say bring in active record multi-tenant, and we also bring in composite primary keys, which we didn't write. It's another gem out there that'll give this capability because we wanted to match more closely the way uniqueness works, and now we can because the queries are scoped properly. But really the key thing is in each of these models, we added multi-tenant store. We're saying this model participates in a multi-tenant system, and its notion of tenancy is the store ID. With that in place, now we can execute queries inside of a context that's going to scope anything and everything that active record generates, any SQL. So what we do is we say multi-tenant, we start it up with a particular store. As we said, we didn't care which one it was. We just picked the first store. We said, with this in mind, now everything is for that store, do these statements. And any queries inside of this section are going to be safe. Not only will they be safe and fast, as we saw, but they actually look a little simpler. Now I just say, go through all the orders, find the one who's most expensive, and then find the product for it. By saying all the orders, it's understood that it's all the orders just for this store. So I didn't even have to write as much code, and it works better. It's kind of win-win. If we look and kind of verify the queries it's making just to see how is this safer, what is it doing? The first query is the same. It's grabbing the stores, pulling that first one out. Then once again, it's finding the orders for the store, the order that's most expensive. But here in the magic, the last one, it's pulling the product. Yes, it's saying product ID is 7. Here I'm not showing the number 7, I'm showing the substitution thing, but it's searching for a specific product ID. But it also put in a seemingly redundant filter on store ID equals 1, and that's where the protection and the speed comes from. You don't have to touch it. That's just the way it makes queries now. So it's great. And it's fast. And we can see how it's fast by looking, once again, asking the query planner, what are you going to do with this query? I say, explain this thing. This is the query I know that active record generated. And now the query planner is showing me task count is 1. It knows it only has to ask one question. And it knows exactly which worker to send it to. In this case, it's worker. So it just sends it to one place. The single machine sends the results back, and it's really fast. So now we've seen that the queries we've generated are safe and fast and easy to use. So go get them. We've created helper libraries for 2 application frameworks, popular ones, Django and Rails Active Record, and with others possibly down the line. They're all in the Citus Data GitHub organization for you to try out. Thanks for watching, and enjoy the rest of the Azure Cosmos DB liftoff.